Greetings, everyone. My name is Darrell Everett Patterson Jr., and I will be presenting on biotic and abiotic carbon capture strategies for decarbonizing Earth's atmosphere, ultimately to mitigate the impacts of global climate change. Thank you for listening. Beginning with direct air capture, or DAC, which is a carbon capture and storage process that involves the removal of carbon dioxide from point sources or Earth's atmosphere through operating powerful turbine fans that ultimately pull carbon dioxide from the air. And once that air is directly drawn from industrial effluent sources like coal and natural gas fired power plants, or indirectly from the atmosphere, it is stored within unminable coal seams in deep saline reservoirs. Limiting factors to consider when regarding this powerful carbon capture and storage approach is that storage capacity, availability, and source for a prospective CSS site, in addition to storage site accessibility, are key contingencies for the viability of CO2 sources in storage locations, and that policymaker assessment of CCS effectiveness and time running influences decision making processes that finance carbon capture and storage facilities with public investments. Thus, what these limiting factors signify is that for policymakers to actually finance carbon capture and storage facilities like direct air capture facilities, it has to be cost effective, meaning that these facilities need to be near point sources where they can derive carbon and also have access to underground locations where the processes that fixate the carbon into a solid material are able to be efficiently and effectively operated. Direct air capture has already exhibited success as a CCS approach to the world's largest DAC facility called Mammoth, located near the capital of Iceland, Reykjavik, and developed by Swiss firm Climeworks, which sequesters approximately 36,000 tons of global warming carbon dioxide out of the air annually. Within this state of the art facility, fresh, highly porous basalt, a sorbent material known as an amine functionalized solid, reacts with captured carbon after CO2 is mixed with fresh water and percolates more than 700 meters underground, forming solidified carbonate materials. The key constant in DAC methods is the reacting of CO2 with a liquid solvent or solid sorbent, promulgating conversion to a non gaseous state, thus merging said carbon into a sorbent substrate instead of the open atmosphere, thereby preventing further planetary warming. With the mounting success of an estimated 19 DAG plants in operation today, the United States of America has taken a bold initiative to invest in DAG plants to mitigate its contribution to the aggregate total of atmospheric carbon dioxide. Although seemingly an afterthought amongst emerging carbon capture and storage technologies, green infrastructure and flora species remain still a formidable option for sequestering carbon from the atmosphere. And according to the Audubon Society, a mature tree can absorb an estimated 48 pounds of carbon in 1 year. Today, carbon stores, known as repositories of Earth's carbon stocks, within the biome of tropical, boreal, and temperate forests, amount to 888, 877, and 569 megatons of carbon dioxide per hectare, respectively, and demonstrate the propensity to accommodate increased flora species, namely trees, through forest restoration and afforestation efforts. Wherever plant growth opportunities exist, landscape design strategies can ultimately be leveraged to provide for biodiversity habitats, human livelihoods, and the sequestration of carbon into soils. In addition to trees and plants, soil stores a lot of the world's carbon in a substance called soil organic matter, or SOM, which is typically 50 to 60% carbon. An innovative approach to afforestation, or planting trees where they've yet to exist within recent relevant history, would be the utilization of a conceptual approach similar to the objective of the 1902 U.S. Reclamation Act, whereby funds can be raised from the sale or occupancy of public land in arid states to be used to construct water storage and irrigation systems. These systems, in return, can combat climate change, induce drought, and water stressed regions and enable afforestation efforts to cultivate forest ecosystems where limitations to the possibility were once seemingly impossible to overcome. Yale School of the Environment's Environmental Leadership and Trading Initiative guest lecturer Robin Chasdon articulated the propensity for forest landscape restoration, or FLR, to regain ecological functionality and enhance human well being in deforested or degraded landscapes, as it is a process and means of regaining, improving, and maintaining vital ecological and social functions that, in the long term, lead to more resilient and sustainable landscapes. These reinvigorated landscapes, through conservation and restoration approaches such as agroforestry and silvopasture, have the capacity to sequester carbon into biomass out of the atmosphere and to limit further global warming. Like conservation, restoration, and sustainable land use strategies in non urban areas, biotic and abiotic carbon capture and storage opportunities through cumulative zoning ordinances offer the opportunity to transform vacant spaces within urban contexts into zones or areas where carbon capture storage technology such as direct air capture or commercial urban agriculture or community gardens play a pivotal role in sequestering carbon from the atmosphere while creating value for communities where these opportunities exist. Under a cumulative zoning ordinance, land that is zoned for a particular use may be used for that particular use in any lesser value use, but not for any higher value use. So, say you have a light density residential community, high value land uses. It would be wise to actually implement commercial urban agriculture or community gardens, as there's less of a nuisance aspect that coincides with that land use development. However, in industrial zones where there's vacant lots or open space opportunities, small scale direct air capture facilities located near industrial power plants or industrial facilities would actually allow for direct air capture that is cost effective and efficient if other parameters are in play in favor of those operational processes. Blue carbon in ocean conservation also presents a viable opportunity for carbon capture and storage, in addition to biodiversity benefits both for the ocean environment and terrestrial environments. Blue carbon refers to the way coastal and marine ecosystems capture and retain carbon dioxide. Estimated to have a valuation of $33 trillion in 1997 by a group led by Constanza, the portion of Earth's global ecosystem attributed to open oceans, continental shelves, and estuaries exhibited the highest total value, while the highest per hectare values went to estuaries, swamps, floodplains, and seagrass and algae beds. It is approximated that mangroves, salt marshes, and seagrass store carbon totals of 933, 593, and 326 megatons per hectare annually, respectively. And as an ideal method for preserving kelp forests against imminent threats, ecosystem based management has proven to be effective in fostering the benefits of carbon capture and storage in the ocean environment. Thank you again, everyone, for listening. This is my reference page, and I hope you learned a lot about carbon capture and storage approaches and technologies because they're actually the key to mitigating global climate change to remain in alignment with the Paris Climate Accord after reviewing the results from the IPCC about how we are already past warming potential and headed into a territory that requires climate action to preserve our planet. I hope you can take part in any way, and I thank you again for listening.